Welcome to Chapter 7. In this video, we're going to define a new coordinate system based on squircles and base P trigonometry. This is the visualization of the coordinate plane that I'd like us to walk away with. To contrast with circular polar, instead of moving by rotating around different sized circles, we should move by rotating around different sized squircles. I'd like you to recall this figure and these equations from Chapter 1. Here, we associated the horizontal leg of this triangle with cosine base p and the vertical leg with sine base p. That makes the xy coordinate pair of the top point cosine base p and sine base p, respectively. Another fact from Chapter 1 is that our trig functions describe the coordinates on a unit squircle, which from Chapter 2 we're able to define as all the points which have a p-norm of 1 from the origin. And from that, we define squircles of any radius r base p using the p-norm. If we combine these four equations, we'll end up with this new one, which is the sine-cosine Pythagorean identity just multiplied by the absolute value of r base p to the p. Using this in combination with the fourth equation, we can rewrite the values of x and y as r base p cos base p and r base p sine base p. So this no longer represents the coordinates of a unit squircle, but a squircle of any radius. I stopped the GIF here so it's easier to see the changes I made to it. The lengths on this triangle are now being measured with the p-norm, as shown by the bottom equation. And by illustrating this, we've taken a huge step to defining squircular coordinates. We have our definitions for x, y, and distance from the origin r base p. The last thing that's required would be a definition of angle. The answer to this is actually simple since we've been using angles in a conventional way throughout this entire series so far. Our angle theta will be arctan of y over x. Something that I want to pose is that x is still x, even in circular polar coordinates, which is squircular coordinates with p equals 2. So r base p cos base p theta equals r cos theta. Expanding the cos base p, we can see that r base p height base p theta equals r. This statement is cool in and of itself, but after moving some things around, you can see another definition of hype emerge. Hype is the ratio of the Euclidean norm, or 2 norm, of x and y to the p norm of x and y. Now I'll show two quick proofs of this definition. The first one we can do is by substituting in our new definitions for x and y. We can factor out an absolute value of r base p from both the numerator and denominator. After they cancel out, you can see that the denominator becomes 1 due to the Pythagorean identities, and the numerator becomes the square of hype squared, something briefly mentioned in Chapter 1. Since hype is always positive, the square root of hype squared is itself. Since we were able to derive the left-hand side from the right hand, we showed that the initial equation is true. If that proof isn't satisfying to you since we used something that we just defined to reach that conclusion, here's another. We'll use the definition of theta as arctan y over x, and we'll replace it. This expression can be simplified using a trick. We can visualize the relationship between an inverse trig function and all the other trig functions using a right triangle. We're trying to take the cosine of an angle whose tangent is y over x, so we can create an angle theta and label the length such that the tangent of theta is y over x. We complete the triangle using the Pythagorean theorem, and now we can find the cosine and sine of the angle using SOHCAHTOA. After simplifying the expression to be over the same denominator, we can apply the exponent -1 over p, resulting in the right-hand side of the initial equation. Up until this point, we've defined cosine as simply the x-coordinate and sine as simply the y-coordinate of a right triangle within a squircle, avoiding defining it as a ratio because that would result in cosine and sine base 2. However, if we move the r base p, we can see that these functions can be defined as a ratio after all. Expanding r base p, it's easier to see that this is the p-norm of the point xy. This is why it seemed like we were only using the x and y coordinates to define cosine and sine base p. Since the unit squircle is all of the points with a p-norm of 1, the trig functions in a unit squircle are just x over 1 and y over 1. Now it would be apt to rewrite this hypotenuse length as the p-norm of xy instead of the 2 norm. With this new perspective, we can not only recontextualize our definitions of the base p trig functions, but the Pythagorean identities. The Pythagorean identities are consequences of the geometry of a vector space equipped with the p-norm. in simpler terms, I'm saying that we're in a space where we measure everything with the p-norm. This goes for the sine-cosine identity, the tangent-secant identity, and the cotangent cosecant identity. If you treat the p-norm like the Pythagorean theorem, you'll end up with Pythag. As a word of warning, this trick with Pythag doesn't work with all right triangles in a p-normed vector space, something that we'll discuss more in a future chapter. Anyway, that's it. We defined the conversions from squircular polar to Cartesian, Cartesian to squircular polar, and defined the relationship between circular and squircular polar. Please comment with any questions you might have because I'm sure to answer them. Bye!